Welcome back. Vectorization is basically the art of getting rid of explicit for loops in your code. In the deep learning era, certainly in deep learning in practice, you often find yourself training on relatively large datasets because that's when deep learning algorithms tend to shine. And so it's important that your code run quickly because otherwise, if you're training on a big dataset, your code might take a long time to run and you just find yourself waiting a very long time to get a result. So in the deep learning era, I think the ability to perform vectorization has become a key skill. Let's start with an example. So what is vectorization? In logistic regression, you needed to compute z equals w transpose x plus b, where w was this column vector, and x is also this vector. And maybe they're very large vectors if you have a lot of features. So w and x were both these Rn or Rnx dimensional vectors. So to compute w transpose x, if you had a non-vectorized implementation, you would do something like z equals 0, and then for I in range of nx, so for I equals 1 to nx, z plus equals wi, times xi. And then maybe you do z plus equals b at the end. So that's a non-vectorized implementation. And you find that that's going to be really slow. In contrast, a vectorized implementation would just compute w transpose x directly. In Python or in NumPy, the command you use for that is z equals np dot w comma x. So this computes w transpose x, and you can also just add b to that directly. And you find that this is much faster. Let's actually illustrate this with a little demo. All right, so here's my Jupyter notebook in which I'm going to write some Python code. So first let me import the NumPy library. So import this np, and so for example, I can create a as an array as follows: 2, 3, 4. And let's say print a. Now, having written this chunk of code, if I hit Shift Enter, then it executes the code. So it created the array a and it prints it out. Now, let's do the vectorization demo. I'm going to import the time library, since I'm going to use that in order to time how long different operations take. I'm going to create an array a equals random dot rand. Let's create a million dimensional array, right, with random the values b equals np dot random dot rand, another million dimensional array. And now tick equals time dot time, so let's measure the current time. C equals np dot ab. Let's see, talk equals time dot time, and let's print. This is the vectorized version, right? So vectorized version, and so let's print out. Let's see, the last time. So let's talk minus tick times 1000, so that we can express this in milliseconds. So ms is milliseconds. Okay, so I'm going to hit Shift Enter. Okay, so that code took about 3 milliseconds, or this time 1.5. Okay, maybe about 1.5 or 3.5 milliseconds that time. So, it varies a little bit as I run it, but it looks like maybe on average it's taking like 1.5 milliseconds, maybe 2 milliseconds as I run this. All right, let's keep adding to this block of code. So let's now implement a non-vectorized version. Let's say c equals 0, then tick equals time dot time. And now let's implement a for loop for I in range of 1 million, right? Hope I got the number of zeros right. C plus equals AI times BI, and then talk equals time dot time. Oops. And finally print, with an explicit for loop, the time it takes is this 1000 times talk minus tick plus ms, just to denote that we're doing this in milliseconds. Okay. Oh, and actually, let's do one more thing. Let's just, print out the value of c we computed to make sure that it's the same value in both cases. Okay, so I'm going to hit Shift-Enter to run this, and check that out. So in both cases, the vectorized version and the non-vectorized version computed the same value. This is 250.286.989, so on. The vectorized version took 1.5 milliseconds. The explicit for loop, the non-vectorized version, took about 400, almost 500 milliseconds. So the non-vectorized version took, something like 300 times longer than the vectorized version, right? And so with this example, you see that if only you remember to vectorize your code actually runs, over 300 times faster. Yeah. Well, let's just run it again, right? Here's run it again. Yeah, vectorized version 1.5 milliseconds, and the for loop took 481 milliseconds. So again, about 300 times slower to do the explicit for loop. So 300x slowdown is the difference between your code taking maybe 1 minute to run versus it taking, say, 5 hours to run. And when you are implementing deep learning algorithms, you can really get the result back faster and iterate much faster if you vectorize your code. So some of you might have heard that a lot of scalable deep learning implementations are done on a GPU, on a graphics processor unit. But all the demos I did just now in the Jupyter Notebook were actually on a CPU. And it turns out that both GPU and CPUs have parallelization instructions. They're sometimes called SIMD instructions. This stands for single instruction, multiple data. But what this basically means is that if you use built-in functions such as this np-dot function, or other functions that don't require you explicitly implementing a for loop, it enables Python and NumPy to take much better advantage of parallelism to do your computations much faster. And this is true both for computations on CPUs and computations on GPUs. It's just that GPUs are remarkably good at these SIMD calculations, but CPUs are actually also not too bad at them, maybe just not as good as GPUs. So you've seen how vectorization can significantly speed up your code. The rule of thumb to remember is, whenever possible, avoid using explicit for loops. Let's go on to the next video to see some more examples of vectorization and also start to vectorize logistic regression.